Hello guys, welcome to my video. So today I'm going to be working the May-June 2016 question paper 1-2 for physics, and the question paper is 1 hour 15 minutes long. And I'm going to be going through some of the questions and how you were supposed to answer them and explaining each and every concept in detail. But if you have a specific question that you'd want to be addressed, I would highly recommend that you just skip, use the timestamps that I've posted in my description, or just you can easily skip to the part of the video that you'd like to watch. But I highly recommend that you watch it all, because I'll be able to explain some of the different concepts and how you were able to think about them. But I highly recommend that you work these question papers out so that you can be able to gain more and be able to understand. Okay. So if you like my content, please like, comment, share, and subscribe, and yeah, so that the channel can be able to grow. Okay. So let's begin. Number one, we've been asked which quantity with its unit is correct. Okay, so let's start with the first one. The first one is acceleration. Okay, so basically acceleration is the rate of change of velocity. Okay, so for A, we know that acceleration is equals to velocity divided by time. Okay, so velocity is measured in, so the units of acceleration, velocity is measured in meters per second, and time is measured in seconds. So the units of acceleration will be ms to the power of -2. But here they've given us ms to the power of -1. So it really can't be acceleration because the units are not aligning. Okay, so the answer can't be A. Okay, move on to B. Electric current in a lamp is amp per second, right? So basically, so if we were to move to B, basically current is basically the charge divided per unit time, the rate of flow of charge. Okay, and charge is measured in AS and time is measured in S. So the units of current would therefore be equivalent to A. Okay, but the units here are A per second, right? Which is not correct, which makes B wrong. Moving on to C, we know that potential difference. Okay, so C, we know that potential difference is the work done per unit charge. Okay, work done is measured in joules, charge is measured in coulomb, so it's joule per coulomb. Okay, making C the correct answer. D, kinetic energy of a car. So kinetic energy is basically energy itself. Okay, so if we're looking at D, the kinetic energy will be 1/2, okay, 1/2 mv squared. M is actually kg, v is actually m squared s to the power of -2. Okay, but here we're given Newton, and Newton is actually, so if we look at Newton here, this is actually kg m to the power of s to the power of -2 divided by m to the power of -1, which is just basically kg s to the power of -2, and that's incorrect. So the answer, which is correct, is actually C. Okay, move on to question number 2. The luminosity L of a star is given by L is equals to 4 pi r squared multiplied by that constant, right? With those units. And the question is asked us to find the SI base units of L. So how do you tackle this kind of questions? Well, the first thing that you need to do is make that thing the subject of formula. Okay, and if we look at this question, L is already the subject of formula. Okay, so let's start with sigma, right? This is basically, we know that power, okay, because this W is the unit for power. Okay, we know that power is basically the force per unit area, and the units of force are kg ms to the power of -2. The units of area are m squared. So here we have kg, okay, because the units of force is that and the units of area is that, so basically have kg, okay, m to the power. So power is basically the work done per unit time. Okay, so work done is basically kg m squared s to the power of -2 divided by time, which is s. Okay, so that gives us kg m squared s to the power of -3, right? Or the watt, famously known as the watt. Okay, so if this is the definition of power and want to find the units of L, okay, so if this is the definition of power and want to find the units of L, how do you go about this? Well, basically, we now know that sigma, okay, so L would be equivalent to the value of r squared, which is basically, so the units of L, the value of r squared, which is actually m squared, okay, multiplied by the value of that sigma, which is kg m squared s to the power of -3 multiplied by m to the power of -2 multiplied by k to the power of -4. And T to the power of 4, temperature is measured in Kelvin, so it's basically multiplied by k to the power of 4. Okay, so these two cancel out, those two cancel out, so basically these two, okay, these two cancel out, and 2 and minus 2, those two cancel out, okay, and okay, what else are we left with? We're left with kg m squared s to the power of negative 3. So the units would therefore be kg, okay, kg m squared s to the power of negative 3. So our answer will be C. Okay, so very important. Make what you want to find the subject of formula, and after you've made the subject of formula, therefore you can just go and be able to figure that one out. Okay, so very important. Okay, move on to question number 3. Diagram shows two vectors x and y are drawn to scale. Okay, so a vector x and a vector y. Okay, if x is equivalent to y minus z, which diagram best represents the vector z? Okay, so with number 3, basically what you need to know is that x is equivalent to y minus z, z is the resultant force. So you've combined vector x and vector y, and vector z is the resultant force. So basically we just want to express it in its due form so that we can be able to assess what exactly is going on. Okay, so if to put z on the other side, we basically have an expression that says that, okay, so if we put z on that other side, we'll basically have an expression that says that z is equivalent to y minus x. Okay, so basically z will be equivalent to y plus negative x. Okay, right. So how do we even go about this? Well, the first thing that I would recommend is you try to draw these two vectors alone. Okay, so the method that we're going to be using is a very simple method. It's known as the head to tail method. Okay, it's a very easy method that you can implement whenever you're solving questions that involve you finding resultant vectors. Okay, so we'll first start with y. So y is basically something like this. Okay, so basically this is our y. Okay, and then the value of x, the vector x, is pointing up. Now once you have identified your vector y, now it's about identifying your vector x, right? So the negative of x, the negative of a vector is just something that has the direction swapped. Okay, so a vector basically has magnitude and it has direction. So the negative of a vector, if it was pointing up, now it's about to point down. Okay, so now it will be pointing down, right? So something like that, right? So how the head to tail method works is you're going to place our first vector y. Okay, so this is negative x. So we're going to first place our vector, okay, like this. This is our vector y. Okay, very important. And then we're going to go to head of vector y. Okay, so this is the head, right? This is the head of y, right? And we're going to go to that head and we're going to put the tail of vector negative x. Okay, so once we go here, we're going to put the tail, okay, right? So basically this, okay, this is the tail, okay, the tail of negative x, right? So the tail is the end of it, like an arrow, right? The back of an arrow, that's the tail. It's like more pointed, but where it's very, very pointed at the top, that's the head. So the head of vector y is that, and the tail of vector negative x is that. So it's head to tail, okay? So if we were to finish this, this is our vector negative x, right? What is our resultant force? The resultant force is basically you go from the tail of the other vector that you've connected. So basically our resultant force, we're going to start here, right? This is the tail of that vector, and we're going to go to the head of the other vector, right? Something like this, right? So once you have connected head to tail, the resultant force will be from the head, okay, from the tail, sorry, of one vector to the head of the other vector. Because if you've connected head to tail, those two vectors are going to intersect at one point, and you're going to connect tail to head of that. So this is going to be your resultant force. Okay, so basically this is going to be your resultant. So we need an arrow that's slanted in that direction and pointing down. An arrow that's slanted in that direction and pointing down has to be option A. Okay, so very important for you to be thinking about this, right? So whenever you're given a vector resolution, you shouldn't be able to fail this question. Okay, so this is a vector question. And how we think about this is head to tail. First state z is equivalent to y minus this, equated, then find the resultant force. Very important. Moving on to question number 4. We'll be given a diagram that shows the cathode ray oscilloscope. Okay, so basically this is a CRO question, right? So question 4 is basically a cathode ray oscilloscope question, okay, that is being used to measure the rate of rotation of a flywheel. So basically, this flywheel is rotating like this, and we're using a cathode ray oscilloscope to measure that rotation, okay? The flywheel has a small magnet M mounted on it, so this is the magnet. Each time the magnet passes the coil, a voltage pulse is generated. So as the magnet passes this coil, you see a voltage pulse will be generated, okay? The display of the cathode ray oscilloscope is basically 10 centimeters wide, okay? So 10 centimeters over there. The flywheel is rotating at 3,000 revolutions per minute, okay? So basically we can find the time taken for one revolution. If it takes 3,000 revolutions for 1 minute, how much time does it take for one revolution, right? So we can easily calculate that. Which time-based setting will display clearly the separate pulses on the screen, okay? So let's go through how we can be able to solve these kind of questions, okay? So basically, it rotates, right? It takes 3,000 revs per minute, right? So basically, the period is the time taken. So the period is basically the time taken for one revolution, okay? So if it takes 60 seconds for 3,000, what about one revolution? So one revolution will basically take 60 divided by 3,000, right? So 60 divided by 3,000 will basically be equivalent to 0.02, which is about 20 milliseconds, right? So one revolution, get this, will take 20 milliseconds. 1 second, but divided it into like 20 milliseconds. A milli is way smaller than a second, right? So one revolution is going to take 20 milliseconds, right? So, okay, so basically on A, this is how it's going to work, right? So if 1 centimeter, right, one pulse was generated in 1 centimeter, it took us 1 second, right? So basically, if we're going to say 1 divided by, that 1 centimeter, 1 divided by 20 times 10 to the power of negative 3, or 0.02, basically, that's going to give us approximately, I think, 50, right? 50 pulses, right? So basically, these are the number of pulses that you're going to make, right? So the period will be, right, because the period will be 0.02, which is 1 over 0.02 will actually be, right, 1 over 0.02, that will actually be 50, right? So you're about to make 50 pulses per every centimeter, which is basically like the frequency, right? Basically. So if you're making 50 pulses per second, which will be like 50 pulses per centimeter, right? It means that you're going to take, right? So if it's the time-based setting, you're going to have 50 pulses in 1 centimeter. So let's go, right? So basically, this might be 1 centimeter. So if we're going to make that division, this is going to be 1 centimeter. But imagine this, you're about to make 50 pulses amongst 1 centimeter. It doesn't make sense. You won't be able to see anything, because in 1 centimeter, you're trying to make 50 pulses, right? But if you go to B, we have 10 milliseconds, okay? 10 milliseconds per centimeter, okay? 10 milliseconds per centimeter, right? And our pulse, our normal pulse, is actually taking 20 milliseconds, right? That's our period, meaning that I only need 2 centimeters, for each pulse, okay? So each pulse will take 2 centimeters. So it's like, this is 2 centimeters, then I see a pulse, right? Which makes sense. Another 2 centimeters, I see another pulse. Another 2 centimeters, I see another pulse. I see another pulse, right? So basically, since I have 10 centimeters, I'm going to form like 5 pulses, which I'm going to detect. And that makes sense, because I can clearly see 5 pulses showing up on this particular cathode ray oscilloscope. But if we were to go to C, let's try for C. Okay, if we were to go for C, you'd realize that C is actually 100 microseconds per centimeter, right? So if you look at C, basically B, okay, 0.02, okay, so 0.02, if we divide it by 1 times 10 to the power of negative 4, right? So we want to find if 0.02 is the time for one period. If I have a time of 1 times 10 to the power of negative 4, how many centimeters do I need, right? So basically, you need about 20,000, okay? No, it's about 200, right? So basically, you'd need about 200, right? 200 centimeters for you to see a pulse, right? Meaning you won't even see a pulse, because you need 200 centimeters. So you need something like this, right? And for your pulse to form, you just see a line being formed on the screen, right? You won't even see the pulse itself. Even if you were to go to D, right? If you were to go to D, you're telling me that you're going to represent 1 microsecond is going to be represented per centimeter. If you're going to divide this 2, since it's 0.02, okay, divided by 1 times 10 to the power of -6, that's basically going to be equivalent to over 20,000, right? 20,000 centimeters. So your time-based setting is saying, no, in 1 centimeter, I'm going to show like these microseconds that will be there, right? But you only have 0.02, meaning you need about 20,000 centimeters because it's so small, right? You need about 20,000 centimeters to show the whole wave itself. Because if 1 second represents 1 microsecond, get this, if 1 centimeter represents 1 microsecond, you need 20,000 centimeters to represent your whole wave, and we don't have that much space, right? So A is wrong because you need 50 pulses for 1 centimeter. That's too much. B is correct because you need 2 centimeters for each pulse. C is wrong because you need 200 centimeters for 1 pulse. So the answer becomes B. Okay, very important. I'm moving to question number 5. Okay, we've been asked what is the percentage uncertainty in the calculated value of the density. So how do you find the percentage uncertainty, right? So number 5 is a question on percentage uncertainties. We know that delta rho divided by, right? So delta rho divided by rho will be equivalent to 0.1. So the fractional uncertainties divided by 6.2, okay, multiplied by 100 plus the other one 0.1 divided by 25.0 multiplied by 100 plus the other one, we take 0.01 divided by 2.00 but multiplied by 2, because look at this power means that you have to multiply by 2. Whenever you see a power in uncertainties, that power symbolizes multiplying by 2. So if you multiply all of this by 100, right, and we compute this, we basically get about 1.61290, 322 plus 0.4 plus 1, that's basically 3.0%, and the answer is D. Okay, move on to question number 6. I've been given the acceleration of free fall on the moon. So we go to the moon, and whenever you drop something, it's going to accelerate at 1.6 meters per second. Now we've been told the moon has no atmosphere. Do you know what this means? It means that if the moon has no atmosphere, there is no air resistance, right? You guessed it. There is no air resistance, right? Okay, no air resistance present on the moon. Basically, because there is no air resistance that is there, right? So basically, right, we know that the gradient, okay, so for number 6, okay, we know that the gradient of a speed time graph, so the gradient of, okay, speed time graph actually represents the acceleration, right? So if there is no atmosphere, the acceleration is not going to change, basically. So the gradient of these graphs should be a straight line, right? So that already eliminates B and C and D, right? Because the gradient here is actually 0, right? The gradient is actually equivalent to 0, right? So if you go here, the gradient is actually 1.6 because the gradient is actually, right? The gradient will actually be the change in speed divided by the change in time, which is 1.6 divided by 1, which is actually 1.6. So the answer is A, right? Very important. So you just find the gradient, right? And you know that your gradient will actually be the value that you want to find, right? Moving to question number 7. We've been given a tennis ball that is released from rest of a tall building. So we have this tall building that you can see over there, and we're releasing a tennis ball at rest from the top of that tall building, right? We've been asked which graph best represents the variation with time t of the acceleration A as the ball falls, right? Assuming that the effect of air resistance is not negligible. So what does air resistance do? Because this is a very crucial statement that we're going to talk about. What does air resistance do, right? As the ball is released, the weight acts downwards, right? So the weight actually acts downwards, and that causes a downward acceleration, right? Because as it's falling down, the weight is going to cause a force, right? So the word acceleration, the word force should be coming to mind, right? But as the ball falls, the upward resistive force due to air resistance acting on the ball actually starts to increase, right? So as the air resistance upwards increases and the weight downwards is actually decreasing, what does it mean? It means that the resultant force downwards will actually start to decrease. So acceleration is going to start at a very high value. So it's going to start at a very high value. This value is actually going to be 9.81, right? So acceleration is going to start at 9.81 and it's going to decrease. Why? Because acceleration decreases acceleration is going to decrease cause air resistance, okay? is also going to increase. So what it means is that the weight minus minus the air resistance will actually tend to zero, right? So acceleration is going to decrease because air resistance is actually going to increase, right? So as that happens, the resultant acceleration would therefore decrease, right? But get this, as the velocity keeps on increasing, this thing is still accelerating, right? But just at a decreasing rate. As the velocity continues to increase, the air resistance will also increase, right? How's this so? If you've ever ridden a bicycle, you know that as you start riding a bike, the wind is going to blow on you, right? So the wind is going to blow backwards. So as the wind starts to blow, that's causing air resistance. The faster you ride your bike, the more the air resistance increases. But if air resistance increases to a certain extent that is equal to the driving force that you're putting in your bike, then you won't have a resultant force. In a similar way, as the velocity begins to increase, the air resistance will also begin to increase. And as the air resistance increases, it's equal to the weight, your acceleration should approach zero, right? So acceleration should actually approach zero, making A correct, right? B can't be correct because it doesn't approach zero. This is a horizontal line here, and that line will never approach zero, right? Very important. Moving to question number 8, we've been given a graph that shows how the velocity v of an object moving in a straight line varies with time t. From t is equals to 0 to t is equals to t. So get this, guys, right? So question easy. So get this, guys. So question 8 is just about understanding what this thing mean, right? So question 8, you basically need to know these three things, right? So the gradient, okay, of a displacement time graph actually represents velocity. Very important, right? And, right, so the gradient of that represents velocity, and the gradient, okay, the gradient of a VT graph actually represents what? Acceleration, right? Acceleration, right? The area, right, the area under a VT graph actually represents displacement, right? So these are very important key facts that you need to know, right? There are always other facts, right, with kinematics. For example, the area under, for example, you know, the area underneath an ST graph has no meaning. The gradient of an acceleration time graph, again, has no meaning, right? So it's very important for you to just think roughly of these ideas, right? So get this. For this question, you have to identify 3 points where the velocity is zero, right? How do I know this? Well, at this point, the velocity is zero. At this point, the velocity is zero. At this point, the velocity is zero, right? And I know specifically that the gradient of an acceleration, that the gradient of a speed, and I know specifically that the gradient of a displacement time graph represents velocity, right? So the gradient of these graphs that I'm going to be looking at should represent velocity. And whenever, get this, whenever the gradient is zero, the line is horizontal, because gradient vertically measures the steepness of something, right? So if it's flat, horizontal, how is that steep? It's not even steep at all. So a horizontal line has zero gradient. So if you start with D, for example, this is, if you draw a line here, that's a tangent. Velocity is actually equal to zero at that point. If you draw here, velocity is actually equivalent to zero at this particular point itself, right? Again here, again here, again here. You have 1, 2, 3. You have 1, okay, 2, 3, 4, 5 points where the gradient is actually zero. It doesn't make sense, right? If you go to B, we only have 1, 2, right? So we only have 1 and 2. That's the only points where the gradient is actually equivalent to zero. It doesn't make sense. If you go to B, the gradient is zero here, and the gradient is zero here. Again, 1 point and 2 point. It doesn't make sense. But if you go to A, the initial gradient here, if you draw a horizontal line here, the gradient is actually zero here. The gradient is actually zero here. The gradient is actually zero here, right? So basically, the velocity is zero at 3 points. But if you were to understand this, how is this working? The velocity is going to increase, right? So the velocity from here is actually going to increase because it's actually increasing up until it reaches this maximum value. So the velocity is going to increase because the gradient here is actually increasing up until the gradient is constant. So velocity would therefore be at max at this point because it's the steepest point that is there. After that, the velocity decreases, right? So velocity decreases up until it reaches zero. So velocity here decreases up until it reaches zero. From this point, If you're starting from this point as our starting point, the velocity is going to increase as we go down here up until you reach the maximum negative value. Increase, reach the maximum negative value. And the gradient is going to start decreasing again until it reaches 0. The velocity is going to decrease until it reaches 0. So the answer is A. Very important. I'll move on to question number 9. We've been given a ball that falls vertically onto horizontal grounds and the ball rebounds, right? The ball is momentum P1 downwards just before hitting the ground. After rebounding, the ball leaves the ground with the momentum P2, okay, momentum P2 upwards. So the ball is in contact with the air for this time, and during this time interval, the average resultant force is 25 newtons. That's the resultant force, right? Which is a possible combination of values for P1 and P2. How do we find the resultant force? So basically, we know that, okay, the resultant force is actually equivalent to the rate of change of momentum, right? So it's basically the change of momentum, right, divided by the time taken, right? So the change in momentum divided by the time taken. Let's start with A, right? So with A, so that is what a force is, right? So how are we going to do this? Well, the easiest way that you can think about this is let going down be negative, right? Let downwards be negative, right? And let upwards, okay, be positive, right? So you have two directions, down negative, upwards is actually positive, right? So let's start with D. We have 0.65 downwards, so we know that change of momentum will be final momentum. So final momentum 0.15 minus the initial momentum 0.65 divided by 0.02. That's basically going to give us, okay, that's going to give us about 40 newtons. Do we have 40 newtons? We actually have 25 newtons, meaning that A and D are wrong because they're just basically going to give me the same answer. It's just different which one do you take to be first, because it's going to be 0.65 minus 0.15, right? Moving on to B. So let's test B. So this is for A and D, right? So for A and D, right? So let's go for B, right? For B and C, it's 0.30 and 0.20. So it really doesn't make sense because the ball is rebounding, right? The flow is not going to do some miracle and increase the velocity of the ball, because remember, momentum is basically mass multiplied by velocity, and this ground is not going to just mysteriously push this ball upwards with a greater force. The ground is not going to do that. So it wouldn't make sense to say that the second momentum is greater than the first momentum. It doesn't make sense, because for momentum to be greater, it means that the velocity either has increased or the mass has increased. But according to my knowledge, the ball is still the same. So the mass hasn't changed. The velocity is also the same. So the answer can't be B, right? But we explain why the answer is C. If you look at C, the final one is 0.20, okay, 0.20. The initial one is 0.30. And if we divide by 0.20, 0.2, that will give us 25 newtons, right? So the answer has to be C. So you must be thinking about this. With momentum, define the direction. Is up positive, is down positive, right? Or in this case, down was negative, up was positive. After that, know that momentum afterwards cannot be greater than momentum before. It just doesn't make sense, right? Because momentum has to be conserved. And if the ground is also absorbing a certain force, the momentum should actually decrease, right? And after that, you calculate the resultant force. You prove that the force is actually 25 newtons, right? Very important. Moving on to question number 10. We'll be given a sphere that falls through the air, right? The graph shows the variation with time of the sphere's velocity, which diagram shows the forces acting on the sphere when it is at the horizontal, when its velocity is corresponding to the point P on the graph. So again, as something falls through air, it's going to encounter what we call air resistance, right? Okay, so as it encounters air resistance, if there's certain conditions, right? So condition 1, so case 1, if air resistance, okay, is equivalent to weight, right? What this means is that you're moving at a constant velocity. Okay, why? Because the acceleration is equivalent to 0. There is no resultant force, right? So let's look at A. The air resistance is actually equivalent to the weight, right? So it basically means that the velocity is constant. It is when we'll be at this point, right? It is when we will be at this point that we can say the velocity might start to be constant, right? Provided that the line actually becomes horizontal after that, right? So it can't be A. With B, we actually said that it's going to fall through air, right? So we can't expect there to be no air resistance, right? So B is going to be wrong because there is no air resistance, right? So there is no air resistance, right? Very important. Let's look at D. At D, very mysteriously, the air resistance is greater than the weight. It doesn't make sense. The air resistance, for it to be greater than weight, it means that your object has to literally be moved upwards, right? So for air resistance to be greater than weight, you have to accelerate upwards. Your acceleration has to actually be increasing. But if you look at this, the gradient of a velocity time graph represents acceleration. And from this graph, as I can see, the gradient is actually decreasing, right? So the gradient decreases up until the gradient actually approaches zero. So I can't really say that, the air resistance is greater than the weight. But in C, I can. Because if the weight is greater than the air resistance, right, it means that if the acceleration is going to reach zero at some point, the air resistance will keep on increasing, right? But it can't be greater than the weight because the object will have to move upwards, right? So the answer is C. Moving to question number 11. We're given a ball of mass m moving at a constant velocity u. It collides with a stationary mass of m. After collision, the two balls travel at velocities v and v respectively in the directions that have been shown. A student writes three equations relating the collision, which the row in the table indicates the correct and incorrect equations, right? So get this, guys. If you look at A, the first equation, mu is equivalent to mv plus mv, the big one, right? So for question 11, we first start with momentum in the horizontal, right? So momentum is conserved in the horizontal. Okay, that's our first scenario, right? If you look at momentum in the horizontal, before, okay, should actually be equal to after. Okay, so before it was mu, small letter m, small letter u, right, is equivalent to. After collision, we have to find this component of momentum for both the masses, right? Because momentum is a vector, right? We can resolve momentum. So this would be m. If we resolve that one, that's actually m v cos of 30 plus, because they're both acting in the same direction, m cos of 40, right? So this would be momentum in the horizontal, right? We can also move to momentum in the vertical, right? So momentum in the vertical, right? Very important. So momentum in the vertical, you go into the vertical. Before, the momentum was actually zero, right? So zero before, okay, should be equal to after. So before, the momentum was zero. After, the momentum is now, this one would be this component acting up, okay? And this component acting down, right? So if we do this, let's start with the component acting up. The component acting up will actually be mv, okay? So mv sine of 30. The component acting down, let down be negative, will actually be big M, so negative big M sine of 40. So basically, mv sine of 40 should be actually equivalent to mv, okay, sine of 30. So these are our two governing equations. We have this equation, okay, and we have this other equation, right? So these are our two governing equations, right? So if you go here, they're saying mu is equal to mv, so mu is equal to mv plus mv. It doesn't make sense, right? Because it's not in the horizontal, it's not in the vertical. It's not even conserved in what direction, because direction really matters, right? Horizontal and vertical. So it can't be A and it can't be C, right? So it can't be A and it can't be C. So the answer can either be B or D, right? And here, mv sine theta, mv sine 30 is actually equal to mv sine 30. That's correct, right? That's correct, because it's basically this equation, right? So this, right, is essentially this equation, right? So that's pretty correct. Mu is equal to mv cos 30 plus mv cos 40. Yeah, that's pretty correct, because this equation is basically that equation, right? So the answer has to be D. Very important. Moving to question number 12. We'll be given a light rod xy that is an object of weight w. at one end. The rod is in equilibrium. Equilibrium means two things. We're going to talk about it. Equilibrium basically means, so number 12, okay. For equilibrium, you have two conditions that you must meet. Number one, the resultant force, okay, the resultant force should be equivalent to 0. How do I ensure that the resultant force is equal to 0? Pretty easy. Create, okay, a closed triangle, right? What does it mean to say create a closed triangle? Basically, it must be cyclic. For example, if I have this vector and that vector and that vector, right? They create a cyclic triangle because I can move around and come back where I started, right? So this basically means that there is no resultant force in this particular instance, right? Because it has created a closed triangle, right? So this is my closed triangle, and that's my condition for the resultant force, right? My second condition, okay, is that the resultant torque, okay, the resultant torque should be actually equivalent to 0, right? So the resultant torque should be equivalent to 0. How do I know that resultant torque is equal to 0? The line of action, okay, of the forces should do what? Should intersect, right? So the line of action of the forces should intersect for the resultant torque to actually be 0. Look at this. If you have this force, right? Let's assume this. If you have that force, maybe, and this force, right? And perhaps you have that force, right? So if I were to extrapolate this force, it would basically be something like this. If I were to extrapolate that force, so no, that won't meet. Let's say it's more like this, right? If I were to extrapolate this force, it would be something like that. If I were to extrapolate this force, it would be something like that, right? So this is where they meet at a point, right? So here they meet at a point. And since they meet at a point, there is no resultant torque. Okay, so these are the two conditions that you must be thinking about whenever you're solving these two questions, right? The first thing is there no resultant force. How do I see that? I must create a closed triangle. The second thing is there resultant torque. If the resultant torque is not there, the line of action of the forces should intersect, right? So let's start. We want to determine the direction of force on the rod at x, right? So since these two are not in equilibrium, basically x has the role of creating a force that's going to balance these things out. Let's first start with A. With A, so the trick thing is we're not given the magnitude of these forces. So I can't really know if W is bigger than R. That's the trick part. But I can try to create a closed triangle regardless of the magnitudes, right? So let's first start with A. So if I'm looking at A, the immediate thing that comes to mind, how I can create my closed triangle is, since this is acting down, okay, so let's do this. Since this is acting down, okay, so if something is acting down here and this is acting up in that direction, so basically, yeah, so basically this should act in that direction, right? So in terms of F, so we have two conditions, F and we have T, right? So FT, right? So in terms of F, it checks out. The resultant force form a cyclic triangle, right? That is pretty true. If we move to B, that force is acting in that direction and that force is acting down, right? So if I have a force that is basically acting down, right, like that, and I have the force that is acting upwards like that, the force that is acting sort of like upwards like that, right? So to create a complete triangle, I'll basically need a force again that is acting up, so it won't add up, right? How is it possible that I can create a closed triangle with this? It doesn't make sense, right? There is no way that you can create a closed triangle. You might be able to, but it wouldn't make sense, right? So it can't be B, right? Because there is no, it doesn't adhere to this resultant force, right? Let's go to C. To C we have something like this, right? And we have something like that, and we have something acting upwards, right? Like that. Yeah, it doesn't make sense. They can't create a closed triangle. So it can't be B and it can't be C. Let's go to D. With D, we can have something like this, sure. And we can have something like that, sure. Something like that, right? And creating a closed triangle, okay. With D, we can have something like this. So D is pointing in that direction and R is pointing upwards, right? So R should be somewhere there, right? So R will be pointing upwards, somewhere there, right? Close triangle, and weight will be acting downwards, right? So yeah, that works. So basically we have something like this, right? So let's clean that up. We have something like this. So it's basically like that. That's your value of that D, and your R can go and extend from here to here, and the value of your weight will actually be down from there, right? So yeah, D can create a resultant force, right? So in terms of F, it checks out, right? But does it check out with T, right? The torque, right? So how do you solve this? You take your force as it is and you plug it onto your diagram, right? So if you take that force and we were to plug it over here, right? Here's our little force, and we're to extrapolate it. Remember, I always say extrapolate these things, right? So if you're to extrapolate it like that, right? And let's go over there and extrapolate this like that. Okay, let's go over there and extrapolate it like that. These three lines will never meet at any point, right? So A does not check out. A does not allow a resulting torque to not occur, right? Resulting torque would therefore occur at A. Because if they're to meet at a point, it means that there won't be a turning point about any point, because the resultant torque is actually going to be actually zero, right? But if we're going to do the same for D, let's try D. If we're going to put a force downwards over here, okay, let's try to extrapolate. If we extrapolating this force, right, something like that. If we were to extrapolate R, okay, it would be something like this. And if we were to extrapolate W, it would be something like this. Yeah, they check out, they meet at a point. So the resultant torque is actually going to be equivalent to zero, right? Very important. So the answer becomes D. So whenever you see these questions, especially questions involving forces, I advise you two things. Just because they adhere to resultant force equal to zero, it does not mean that the object is in equilibrium. You need to check those two conditions, resultant torque and resultant force, right? I'll move on to question number 13. We're given a large oil container in a refinery, and three oils of different densities are actually being mixed, and no chemical activity actually occurs. The mixture contains 1,200 kgs of oil at that particular density, 1,500 kgs of oil at that particular density, and 4,000 actually kgs of oil at that particular density. So for question 13, I need you to be thinking of these things. That this is a topic that has been coming up a lot. So think of this. This is called density of mixtures, right? So how do you find density of mixtures? The method is pretty simple. It's one method only, right? So the density of a mixture will be equivalent to the total mass of all your mixtures divided by the total volume, right? Okay, that's the formula that you need to know. For density of mixtures, that's all you need to know. So I would advise you, if you're writing somewhere down, just write down that formula. That under density of mixtures, I need the total mass divided by my total volume. There are other methods, for example, fractional densities and trying to work that out, but I would highly recommend that you do it in this way. So simple and plain, and you can be able to get more mass, right? So the total mass, let's first start with the first one. The total mass will actually be equivalent to 1,200, right? So that would be equivalent to 1,200 plus 1,500 and 4,000. 1,500 and 4,000, right? So it's going to give me a total of approximately 6,700, right? 6,700 kgs. The second thing, let's go. Total volume, right? Total volume. Okay, so how do I find volume? I know that total mass, I have it. Total volume. Well, total volume is actually mass. So volume is actually mass divided by the density. So the mass divided by the density. So let's go. Let's first start with the first one, right? So first one is 1,500 divided by 800 and 60. That's 1,100, and that's 910. Okay, so 1,500 divided by 800 and 860. Okay, so 860. That's going to basically be 1.74, right? The next one is going to be 1,200 divided by 1,100, right? That's going to be about 1.09. The next one is going to be 4,000 divided by 910. That's going to be about 4.40, right? So the total is actually going to be 4.40 plus 1.74 plus 1.09. Therefore, we can go back here and actually say now our density will actually be equivalent to 6,700 divided by 4.40 plus 1.74 plus 1.09. Basically, it's going to give you an answer of roughly 927, right? 927 is going to be A. So density of mixtures, you only need one formula. Find the total mass, divide by the total volume, and you get an answer. Very important. Question 14. Two coplanar forces act on the rim of a wheel. The forces are equal in magnitude, right? So which arrangement provides only a couple? So the arrangement that provides only a couple you need to adhere to certain conditions. Number one, they need to be, so this is for question 14. So for a couple, you need a few conditions, right? They need to be opposite, right? Opposite in direction, right? That's number one. Okay. Number two, they need to be of same magnitude, right? Right, same magnitude, okay? Number three, they need to basically be separated, okay? Separated by a distance r, okay? So they need to be opposite in direction, same magnitude, and separated by a distance r. So let's start with A. Are they opposite in direction? They're not. One is up, one is down, so it can't be A. To B, same direction, so it can't be B. With C, one is down, one is flat, it can't be C. With D, are they opposite in direction? They are. Same magnitude, they pretty much look as if they are because we've been told that they're equal in magnitude. Are they opposite in direction? They are. Separated by a distance r. Yeah, they are. So the answer is D. Move on to question number 15. The density of air decreases almost linearly with height, right? So it's almost linearly. Very important to pay attention to details, right? What is the question trying to say? And a lot of it comes from paying attention to particular words within the question, right? With height from 1.22 to 0.74 at an altitude of 5,000. Atmospheric pressure at the Earth's surface on a particular day is 100,000 kilopascals. The value of G between the Earth's surface and an altitude of 1,000 or 5,000 can be considered to have a constant value of 9.7. What will be the atmospheric pressure at an altitude of 5,000? So I need you guys, whenever you see questions that you don't understand, especially questions that are very complicated or times very difficult to understand, I highly encourage that you draw diagrams, right? I highly recommend it, right? So for question 15, let's draw this diagram and try to analyze what this means together, right? So for question 15, let's first start at the ground, right? So we're going to start at the ground where we are at the surface of the Earth, right? So basically we're going to start at the surface of the Earth, right? So basically, this is the Earth's surface, right? So the Earth's surface, right? So we'll be told that the pressure at the Earth's surface is 100,000 pascals, right? So it's 100,000 pascals, right? But what does pressure on the Earth look like? What does it mean to say that we have pressure on the Earth? Remember, the Earth has an atmosphere, and that atmosphere has air, and air has weight, right? So that causes a pressure because, let me just take a column of this, like, let me just take a column so that you can be able to see this. Let me take this column, right? Maybe from here, okay, up until here, right? So if I take this column of air, you agree with me that in this middle, you're going to have this air, right? That will be over here. Okay, so basically, this is air that's going to be present, and that air is going to be pressing down, right? So we just say this is all the air that we have, right? So this air is going to press down over here, right? So this is air, and that air is going to press down, but it's going to cause a force, right? Over a certain area, So this is the force F that is going to cause, but this is over a certain area A, right? We can agree on that, right? Because that's going to cause a pressure, which is going to be 100,000 pascals. And how far does it extend? Well, as big as our atmosphere. That's how long that column of air is actually going to be. Okay, and to be told that the value of density at this point, the density at this point is actually going to be Where is the question? The value of density at this point is going to be 1.22, right? So the value of the density at the surface is going to be 1.22. But get this, we now want to find the value of G at an altitude of 5,000. So we're going to go up to 5,000, right? So we're basically going to be here, right, at this particular point, right? And say at this point, we now have this column of air that'll be over here. Where does this column extend? As far as the atmosphere, right? As far as into space. That is the weight of air that will be there, right? So this column at 5,000 is going to have a certain pressure. We know that pressure increases with the height that you have, right? So at this point, you can agree that at this point, okay, so at this point, there's going to be a certain pressure, P. That's what we want to find, because this air is going to press down a certain point that I've just labeled at 5,000 meters, right? It's going to cause a certain pressure at that point. Is it making sense? So if we're to find, right, so let's extend it. If we're to find that density, right, the density at this point is actually, the value of the density is 0.74. The value of the density is actually 0.74. But I don't know how I'm going to find my value of H. Remember, the atmosphere extends as far as it can go. We don't know the value of H because the value of H essentially is just this height, right? This is your value of H, but you don't know that value of H. But why am I so interested in the value of H to begin with? Why? Because pressure is rho GH. The pressure in a liquid or in a gas is rho GH. So if I have the height, I can find the pressure because at 5,000, I can find the pressure. That's what I want to find, but I don't know the height H. How do I solve it? Well, I can consider going from the ground up to 5,000. So I can consider this portion of air, right? And at this level, I'll be at 5,000, right? So it's at 5,000, and I can just consider this portion of air alone, right? So this is the portion that I'll be considering. Okay, very important. And I want you to get this. This portion is going to cause a certain pressure on the ground, a certain force on about a certain area, right? So you can agree that pressure will be there, right? But it's different from this pressure in the first system because this is system 1, system 2, system 3. You can agree that system 3 has the least pressure amongst all the systems, right? So if I find the pressure in system 3, I know that minus the pressure in system 1, which is 100,000, I'll get the pressure in system 2 because in system 2 is just going from where I left off in 5,000 going upwards, right? That's the whole air that I have. So how do I find the pressure in system 3? Very exciting, right? So how do I find the pressure in system 3? Pressure, we go again. Pressure is actually H rho G, right? What is your value of H? 5,000 times your density times the value of G, which is actually 9.7. So the value of G is actually 9.7 multiplied by 9.7, right? So very important for you to be thinking of that. But get this, guys. We don't know what the density actually is. It's very important, right? Because we've been told that the density decreases almost linearly with height. So if I were to ask you, what is the density of this air that I've just shaded in yellow? You won't give me a value because there's a lot of points that you can take as frame of references. What do I mean by this? Well, if you're at this point, if you take this column of air, it has a certain density that it has, right? Let's assume that the density is 1, right? If I were to take another portion, a portion may be here. It's going to have a different density. If I'm going to take another portion over here, it's going to have another different density. If I'm going to take another portion here, it's going to have a different density. So these portions will keep on having different densities. So I don't know what density I'm going to use. So what do? I find the average. If at that point is 0.74 and at the ground is 1.22, the air in between has to just be an average of that. Because on average, I can say, okay, if at the top is 0.74 and the bottom is 1.2, on average, it's going to be 1.22 plus 0.74. So my density, that's going to be 5,000, okay, multiplied by 1.22 plus 0.74 divided by 2 multiplied by 9.7. That's going to be 5,000 multiplied by, okay, 5,000 multiplied by that average is going to give me about 0.98, okay, 0.98 multiplied by 9.7. 0.98, get this, that's why I found the average. It basically means that 0.98 is the average density of that A that I expect to find, because I took 2 points. If I knew more points, I'll just say I add up all those points and divide by how many points I have. That would be more accurate actually. But since I'm given 2 points, the average density, because any thick column of air that you take will have a different density, because air, the density is actually decreasing. It's 1.22 here, but it's actually decreasing as we go up. So it decreases. So I can't say it's 1.10. It's one. I don't know, right? At this point, it could be 1.2, 1.08, 0.9, and it's 0.74. So to find the density of that air, I have to find the average. So this is going to give me an answer of approximately 48,000 pascals, right? So if this is going to cause 48,000 pascals, and before here is going to cause 100,000 pascals, so the pressure, basically, so the pressure at 5,000 is going to be what, right? 100,000, okay? Subtract 48,000, okay? That's going to give you what? 52,000 pascals, and our answer will be C. Right? So very important. It was a bit complicated, but if you just understand that pressure differs, right? And the hardest part here was understanding that this is the average density that I need to work with, right? Very important. Number 16, a parachutist is falling at a constant terminal velocity. So constant terminal velocity basically means kinetic energy does not change, right? So KE does not change. That's basically what it means to say terminal velocity, right? So the gravitational potential energy cannot be converted into kinetic, cannot be converted into kinetic. It will only be converted into, let's see. Sorry. So it at a constant velocity, meaning the parachutist, the kinetic energy of the parachutist does not change, right? So in D, it's converted to thermal energy of the parachutist. That might happen, right? Because the parachutist might heat up, because gravitational energy is converted into thermal energy, right? It might be converted into thermal energy of the air, might be possible, but kinetic energy of the parachutist, this is my correct answer. This will not happen because the parachutist has to fall at a constant velocity, meaning that the kinetic energy should not change for the parachutist, right? For A, kinetic energy of the air might move, right? It doesn't matter because it's not even part of the system, right? The air might actually be moving down or up, it doesn't matter. But very important, the kinetic energy of the parachutist will not change. It will not change. If it changes, it won't be constant terminal velocity. Very important. Question 17. We'll be given a boy who's on a bicycle and starts from rest and rolls down a hill inclined at 30 degrees, right, to the horizontal. So let's draw a boy over here. So we have our inclined plane. So this is question 17. Okay. So for question 17, we have our inclined plane. So this is our inclined plane. Something like this. And the inclined plane is actually at an angle of, so let's see. The inclined plane is actually at an angle of 30 degrees, right? So let's make it a bit smaller. So the inclined plane is like that at an angle of 30 degrees. And we've been given a boy on a bicycle. As you can see, that's the boy on the bicycle. And the boy and the bicycle have a combined mass of 25. So that boy and that bicycle have a mass, okay? So heading downwards, they have a mass of 25 kgs. There's a frictional force 30 newtons, which is independent of the velocity of the bicycle. What is the kinetic energy of the boy and the bicycle after rolling 20 meters down the slope, right? So we need to find two things. Let's first find the gravitational potential energy of this boy, right? So the gravitational potential energy, the change in the gravitational potential energy, right? So delta GPE is usually going to be mgh, right? What is the mass? 25 multiplied by 9.81. The height is basically this height h, right? So this is the height h that we want to find, and this is 20 meters, right? So how do you find h? It's actually 20 sine of 30. So it's going to be 20 sine of 30. And that's going to give us an answer of 2,452.5 joules. That is my gravitational potential energy. But this thing is actually sliding down because it's actually rolling down a hill, meaning that the gravitational potential energy is converted into something else. But what? We don't know what it's being converted into, right? But we'll find out from our question. It's being converted into work that is used to overcome the frictional force. So it's actually going to be used against, so let's do this. Work done against frictional force is going to be the force multiplied by the distance, right? The force is actually 30, the distance is actually 20, that's actually 600 joules. If 600 joules is going of the gravitational potential energy is going overcoming the friction, what is going in changing the kinetical energy? So the change in kinetic energy would therefore be 2,452.5 subtract 600, right? That will give me an answer of 1,852.5 newtons, right? Approximately 1,850. So you need to be thinking of this, right? Whenever you're dealing with these kind of questions, the kinetic energy has to be conserved. If gravitational potential energy is changing, it needs to go to what? Frictional. But some of it has to go to kinetic because energy can never be lost or gained. Move on to question number 18. We're given an accelerator, an escalator that is underground, that is an underground station with 250 people that are standing on it, and it's moving at a velocity of 4.3 meters per second. Okay, so if you haven't seen an escalator before, I'm showing it right now on the screen. That is what we call an accelerator. Okay, if you haven't seen an escalator before, I'm showing it on the screen right now. That is what we call an escalator, right? So basically, an escalator is just used for stairs, right? So that people will go up much easily. They just get on the stairs and they start moving upwards, right? So we have 250 people that are standing on that escalator, right? 250. So those 250 people will cause a certain force going backwards, right? Because the average person has 78 kgs acting down, okay? So since it's moving up, we need the minimum power to lift these people up because they're moving at a constant velocity of 4.3, right? I know that power is actually equivalent to my force multiplied by my velocity. But these people are going to exert a force downwards, right? This angle, theta, right, is actually 40 degrees, right? So that angle theta is actually 40 degrees. Okay, so my force will actually be, if I have 250 people with a mass of 78 at an angle of sine 40 multiplied by 9.81, which is my value of G, that should be my force because those people are going to exert a force down on the plane, right? You know that if you resolve this, their weight will be downwards. So the weight on that plane will be mg sine theta. But there's 250 of them. That's why I need to multiply by 250. If I multiply by the velocity of 4.3, I should get a power of approximately 122,960, okay, something like that. 558 times 4.3, okay, that's going to give me about 530 kilowatts, right? 530 kilowatts, and my answer is going to be C. Okay, so very important, right? So find the diagram, do diagrams. I highly recommend that you do diagrams so that you can really visualize how these things actually work, right? So this is question 18, right? Very important. Moving on to question 19. An electric motor is operating a lift and has an output power of 20 kilowatts, right? How long does it take if the lift and the passengers have a combined mass of 1,500? What are we doing really, right? We know that power is actually the work done, okay, per unit time, right? So our time is actually going to be our work done divided by what? Divided by our power. But what work are we actually doing, to be honest, right? The work that we're doing is we're lifting up the lift and its passengers upwards, right? So it's 1,500 multiplied by, since the weight is actually 9.81, multiplied by 20. We're doing work in overcoming the gravitational force caused by the weight of these people. right? And we divide by the power, which is 20,000. We should get an answer of approximately 14.715, which is about 15 seconds, right? So the answer is going to be B, right? So very important for you to be thinking of that. Move on to question number 20. We'll be given a spring balance that consists of a spring of length 20 centimeters, right? So the initial length, L0, is actually 20.0 centimeters, right? When a fish of mass 3 kgs is hung and suspended from the hook, the length of the spring is 27.0 centimeters. So as you can see over there, I've hung my fish and my extension, my length actually increases. My spring becomes longer. Okay, and I want to find the value of the spring constant. So this is basically a little bit about Hooke's law, right? So with Hooke's law, we know that F, okay, so we're just going to rush through it. We know that F is equals to Kx. So the value of K will actually be the value of F divided by X, right? So the fish is going to be 3 times 9.81 divided by the extension, which is 7 times 10 to the power of negative 2. Why? Because it's 27, subtract 20, right? So that's where I'm getting this 7 times 10 to the power of negative 2. That's going to give me a value of K of 420 Newton per meter, right? 420 Newton per meter. So this is coming from saying, okay, 27 times 10 to the power of negative 2, subtract 20.0 times 10 to the power of negative 2, right? L2 minus L1, right? Which would be the value of my extension X, right? So just be thinking about that, of where that comes from, right? So the answer is D. Move on to question number 21. Metal wire is attached at one end of a fixed point and a load is hung from the other end so that the wire hangs vertically. The load is increased from 0 to 20 newtons, and this causes the wire to extend by 5, right? So by 5, the load is then reduced to 12, okay, so to 12 over here, and then the extension decreases to 3. How much strain energy is released during the unloading process, right? So basically there are two methods. The first method, you can find the area underneath this region, right? That trapezium, right? But I'm going to go through a much easier step that's going to just make sense because, you have to understand these things like fundamentally, right? So strain energy, essentially what it is the area, okay, of a force extension graph, right? So the area of a force extension graph, right? So it's basically half F multiplied by X, right? So the beginning one, so strain 1, which is my beginning, is half my force being 20 times 5.0 times 10 to the power of negative 3. That gives me 0.05 joules, meaning that at 0.05 joules to go from this point up to that point, that is my strain energy that I'm storing in my wire, okay? But also I can find S2, which is how much strain energy do I have stored in that wire at this particular point, which would be 1/2. My force is 12 multiplied by 1/2 multiplied by 12 multiplied by 3, okay, multiplied by 3.0 times 10 to the power of negative 3. It's going to give me an answer of 0.08 joules, right? So 0.18, sorry, joules, right? So how do I now find the strain energy released? It's the difference, right? If I had 0.05 at this point, but I've arrived at that point and I have 0.018, the difference of those two has to be the strain energy that I've released, right? So strain energy released, okay, so strain released has to be equivalent to 0.05 subtract 0.018. That's going to give you an answer of 0.032 joules, right? 0.032 joules, and the answer is D, because this in standard form is actually 0.032, right? So very important. So okay, move on to question 22. We're given a cathode ray oscilloscope. So these are actually two questions that we've seen regarding the cathode ray oscilloscope, right? So the time-based setting is 0.5 milliseconds per centimeter. So on a cathode ray oscilloscope, this axis going here, this is your time base, right? So that's your time base. That's where you read off the time going up, okay, from this point going up here. That's actually your Y gain, okay? So Find the amplitude and find the frequency. Okay, so frequency is basically, okay, so frequency is basically 1 over the period t. But our period t is actually the number of divisions, okay, the number of divisions for one cycle, right, multiplied by the time base setting, okay, the time base setting, right? So t will be how many divisions do you have? So basically, if I'm starting here, right, and I end here, it's basically 1, 2, 3, 4, 5, and 6, right? So I have 6 divisions multiplied by my time base setting, which is 0.5 milliseconds per centimeter, which is 0.5 times 10 to the power of negative 3. So if I were to do that, it's 6 times 0.5 times 10 to the power of negative 3, okay? That's going to give me 3 times 10 to the power of negative 3. Hence, okay, hence my frequency f is now going to be 1 over 3 times 10 to the power of negative 3. Okay, so it's just 1 over that particular answer, and it's going to give me 333.3, right? So it's 333.3, which is either A or B, right? So A or B are the one that is the frequency of 330. Okay, so C is out and D is out. The next thing is the amplitude. How do you read off an amplitude? Amplitude is basically the distance moved from the equilibrium position. So since the lowest one is here, and I have 1, 2, 3, 4, 5, 6 going up, it means that at the third one here, this is going to be my equilibrium position. So my amplitude is actually going to be 1 here, 2 there, and 3 there. So it's actually going to be 3. So my amplitude, okay, it's basically going to be 3 multiplied by 0.2, which is going to give me 0.6, right? So this amplitude is actually going to be 0.6, and the value of the frequency is going to be 330, right? Very important for you to be thinking of that. Moving to question number 23. A source of sound of frequency 1000 hertz moves away from the source of a stationary observer at a speed of 30 meters per second. The speed of sound we're given 330. What is the frequency heard by the observer? This is basically Doppler's effect, right? If you don't know the equation, I highly recommend that you go back here. Okay, this is the equation for Doppler. Here. Okay, so if you don't remember the equation, just go back, get that equation, and insert it, right, and start working out, right? So with Doppler equation, it's just a matter of you identifying variables, really. That's all Doppler effect is all about, right? So for question 23, it's basically the observed frequency is going to be that frequency V over V minus Vs, right? So what is our initial frequency? 1000, okay? And the speed of sound is actually 330 divided by 330 plus 30. So with Doppler effect, we've been told that it moves away, okay? Moves away. So with Doppler effect, you just need to understand these two things. If it moves away, okay, the frequency decreases. But how does the frequency decrease? You have to divide by V plus Vs, right? V plus Vs over here, right? Plus or minus, sorry, over here, right? And if it moves towards, okay, if it moves towards, F actually increases. So you have to divide by V minus Vs. Why is this? If you divide a fraction, you must agree, if you divide a fraction by a smaller denominator, the answer is bigger. If you divide by a bigger denominator, the answer is bigger, of course. If you divide by a smaller denominator, your answer is bigger. So you have to understand that with fractions, if you divide with a bigger denominator, your answer is very small. If you divide with a smaller denominator, your answer is very big, right? So this one will give me a fraction if the denominator is greater than 330. And you give me a whole number if the denominator is actually smaller than 330. But this one would basically give me a frequency of 917 hertz, right? So with elimination, C and D were supposed to be wrong because it can't be greater than these ones if it's moving away. The frequency is going to decrease, so it has to be B. Okay, very important. Okay, so guys, basically there are ranges with these things, right? So electromagnetic spectrum, I highly recommend go on the internet, research what are the different frequencies that are there, and then you memorize them, right? You just have to know these things by heart, right? There is no shortcut to memorizing these frequencies, but I'm just going to give you some of them, right? So that you can be able to answer these questions, right? But there can always be other on the internet, there can always be others in the test book, but it's important to maintain a specific range when you're dealing with this, right? So we use this abbreviation, okay? So, okay. Right, so all of these are our frequencies, right? And I know that as I go down, the wavelength decreases, right? So wavelength, as I go down, actually decreases, right? So radio basically lies, there are very different ranges for these things, but I'm just going to give you some of them. Radio lies basically from 1 to about 10 to the power of 6, right? But it's just greater than 1 or greater than 0.1, right? So the easiest one for you to just memorize, if it's greater than 0.1, okay, most probably is radio, right? If you go into microwave, it's basically from 0.1 up to, okay, so with radio, if it's basically greater than 0.1, yeah, it's basically going to be radio, right? So if it's greater than 0.1, yeah, meters, it's going to be radio. For microwave, it's basically from 0.1 to about 1 times 10 to the power of -3, right? That's going to be micro. Then for infrared, it's basically going to be from I think 1 times 10 to the power of -3 up until 7 times 10 to the power of -7, right? For visible light, it's going to be from 4 times 10 to the power of -7 to 7 times 10 to the power of -7. Okay, for ultraviolet, it's basically going to be from 4 times 10 to the power of -7 to 1 times 10 to the power of -8. Okay, very important. For X-rays, basically going to be from 1, okay, so from 1 times 10 to the power of -8 to 4 times 10 to the power of power of -11, right? But they can always be -13, -12. These things overlap, right? So they won't be that ambiguous. If it's X-rays, they would just give maybe like 10 to the power of -10. That you can specifically say, no, that's X-rays, right? But they won't give you something like 10 to the power of -12. Those are shady. You don't really know if they're X-rays and gamma because they are overlaps, right? That's why they can really just give you things which are very straightforward. If it's radio, they give you very greater than 0.1. So they can easily tell that this is radio, right? And this is going to be basically from 1, this is 1, right? So here, it's only 1 times 10. So it's 1 times 10 to the power of -11 to 1 times 10 to about -16. But it really extends to -14 or negative that, right? So if we look at here, this is 10 to the power of -9 for gamma. Gamma should be between 11 and 16, so it can't be A. For B, microwave is 10 to the power of -5. Microwave is between 0.1 10 to the power of -3. It can't be B. For C, ultraviolet is 10 to the power of -8. Ultraviolet, yeah, it can't be. Let's see. Let's see. Then the answer has to be ultraviolet, because ultraviolet lies between 4 times 10 to the power of -7 to 1 times 10 to the power of -8. Yeah, so it has to be ultraviolet, right? And X-rays, 10 to the power of -14, that has to be gamma. It can't be D. So you see, it was very it wasn't that much ambiguous, right? You could have said 10 to the power of -8 belongs to X-rays, right? But it's not there. They always give you a question where it's very simple. If you know the steps of what the wavelengths are, they'll just give you a question that aligns with that particular thing, right? Very important. Move on to question number 25. We'll be given a stationary wave that is set up on a straight string. The diagram shows the string at 2 instances, right? One instant and then the other instant when it has maximum displacement. The oscillation of P on the string has an amplitude A. What is the distance moved by P from position shown in the diagram after half a period of the wave? So, basically when it comes to these things, you basically even need to understand what is a period, right? So, with periods, they occur in 4 phases, right? So we have an equilibrium position over here. If you've seen a pendulum, I assume you've seen it, but if you haven't, I'm showing it right now. A pendulum moves forward right, we say that's 1, right? So as the pendulum moves over there and arrives at that position, we say that's the first one. As it goes back to the equilibrium position, we say that's the second one, right? As it goes back over to that position, we say that's the third one. As it comes back to the position, that's the fourth one. So whenever it comes to oscillation, we have 4 phases, right? It starts where it is, it moves to other point, comes back, moves to the other point, and comes back, right? So the same can even happen with time. It's going to move up, right? That's what? Phase 1. It's going to come down. That's what? Phase 2. It's going to move down in the other direction. That's what? Phase 3. Then it's going to come back up. That's what? Phase 4. So oscillations occur in 4 phases, right? And the period is basically those 4 motions. So if a question is telling me half a period, what does it mean? Only 2 motions from where you are. So if I'm starting here, right, half a period looks like this. Half a period, so this is question 25. Half a period basically looks like this. So if I'm here and I have an amplitude of A, when I'm here, right, I assume this is my equilibrium position, okay? Like that, right? So it means that if I'm already at A over here, if I'm moving up, that's A, right? And if I move up again, that will be another A. So basically I've moved a distance of 2A, which is C. Because it remember, I said it occurs in 4 phases. Half a period is just going to be, you start at P, you move up again, 2 phases. You arrive at that, you calculate. If I had amplitude A, and that was the amplitude A, those 2 would be giving me an amplitude of A. Because the question said distance, right? The displacement will be 0, because guess what? It's actually negative A here, right? But in terms of distance, it has actually traveled A and A until it reaches back to its original position, right? Which tells me is an example of diffraction of light. The addition of amplitudes of 2 waves which are in phase, this is interference, right? And more so constructive interference, because the waves are in phase, right? So this word in phase symbolizes constructive interference. The change in direction of a beam of light when it passes from air to water, this is actually refraction, right? Because it's the bending of light as it passes from one medium to another of different optical densities. The separation of a beam of white light into a spectrum of colors using a prism. Newton discovered this, and it's actually known as dispersion. The spreading of white light is scattering out into a different spectrum of colors, right? And the spreading of a beam of white light as it passes through a small hole, guess what? That's diffraction. The spreading of light, as you can see on the screen, the spreading of light into the geometrical shadow as it passes through a small hole. Move on to question number 27. Sound waves of wavelength lambda are emitted by a loudspeaker, and they pass through 2 slits, slit P and Q, and the 2 waves meet at point R. Okay? What is the condition for an intensity maximum, a loud sound, to be heard by a microphone at R? So, yeah, it's just about conditions of interference. Guys, with paper 1, it's about understanding this concept. Right? They basically ask roughly the whole syllabus. So you have to know this concept very well. I would highly recommend, if you are looking for the conditions of intensity maximum, go to your course book, right? Go online, go on notes, understand the concept. Then these questions will become much relatively easier to solve. For example, here they're saying the conditions of an intensity maximum, a loud sound to be heard at point R. What do I basically need at point R? Right? For me to have an intensity maximum, the wave need to meet in phase, right? They basically need to meet in phase. If they meet out of phase, I have an intensity minimum, right? Number 1. Number 2, since this is constructive interference, I basically need a phase difference of 0, 360, and multiples of 360, right? I keep on going and going, right? And then 3, I need a path difference of basically lambda, right? 2 lambda, 0, 3 lambda, right? That's my path difference that I'm going to need. So the amplitude of the 2 waves must be the same. They will always be the same for us to have intensity maximum, but that's not a condition that we need to meet. Because we can still have a maximum with different amplitudes. It can still occur. So it can't be A. Why isn't it B? The distance PQ must be smaller than wavelength. How is that even going to affect the maximum? it doesn't make sense, right? Because reducing this distance really isn't going to change what you're going to see, because waves are going to travel here still, and the other waves are going to travel from here, okay? And those two waves, the other wave is going to travel from here, okay, and meet there. And those two waves are going to have constructive interference. So the distance PQ really has no impact. The two waves must travel the same distance to R. They will never travel the same distance. That's why we even talk of path difference, showing that their paths are actually different, right? So the distance will never be the same, because this point R is more closer to P. This is actually shorter, right? And this is actually longer, right? So it can't be the same. And the answer will be D. If they meet in phase, like I've said, if they meet in phase, it's most likely to be an intensity maximum. Very important. Move on to question 28. Coherent light passes through a double slit, okay, producing bright and dark fringes on a screen placed parallel to the plane of the double slit. The intensity of the light from each slit is initially the same. So the intensity is basically the same. So let's draw this, right? So we have this particular scenario, right? We have that. So sorry. And then we have, this is our value of A, okay? So this is our value of A, right? And then we have a screen. Let's put a screen over here that we'll be using for detecting, right? This is our screen, right? And the intensity of light coming from each slit is initially the same. So I have light coming here that will meet there, and light coming there, and the intensity is initially the same. But the intensity passing through one slit is now increased. So the intensity passing through this slit, okay, so basically passing through this slit, okay, intensity is actually increased. What is the effect on the appearance of the fringes on the screen? Guys, I need you to get this. What causes these fringes to appear is one thing only, and that is interference, right? So if it's constructive interference, the amplitude give me 0, right? Meaning that if I'm going to have a dark fringe, right, my amplitude is going to be the amplitude of the other wave, subtract the amplitude of the other wave, they're going to give me 0. If it's going to be a bright fringe, it's going to be the amplitude of the other wave plus the amplitude of the other wave, and it's going to give me 2A. So I'm going to see a bright fringe because there's an amplitude of 2A. But if I increase the amplitude of one wave, I know that intensity is directly proportional to Ka squared. That's why I said I'm increasing the amplitude of the other wave. Because if I increase the intensity, I'm going to increase the amplitude also. How so? Well, if I increase the intensity to 4i, my amplitude is going to just be 2a, right? So if I were to increase my intensity, right? So basically you don't even need to put values, but just know this: as you increase your intensity, your amplitude will also increase, meaning that the amplitude coming from one wave, is going to be greater, but the other wave is going to be less. So this might actually be greater, but coming from one wave is actually going to be less. So you might say that the amplitude here is 2a, but the amplitude here is just a. So we can now go and say, for me to have a bright fringe, it's going to be 2a plus a. That's going to be what? 3a. So the bright fringe is going to be more brighter. So the maximum intensity of the bright fringe is going to be brighter. If I go to dark fringe, 2a minus a, which is going to be what? To be a. So I once had 0, okay, but now I have a. What does it mean? The maximum intensity of dark fringes is going to be greater, okay? It's going to be greater. But the separation of the fringes, guys, the separation of fringes can only be altered by 3 things. We know that, okay? We know that lambda is actually ax over d. The only thing that can change this value of x is this value of a or this value of d. But that's not changing. I'm changing the intensity of my wave. That's it. So the value of the separation will remain the same. There will be no change, but this will be greater. The answer will be C. Question 29. Okay, this is a question on electric fields. Okay, so this is a question on electric fields. And if you're doing the syllabus from 2022 going onwards, they will removed from our syllabus and moved to A2. So I will not be covering this in this video. Question 30 is also electric fields. Question 31 again is also electric fields. Okay, so let's start with question 32. Which graph represents the variation of an IV of a filament lamp? Basically, it's going to be A. And as you can see over there, I've given you the graphs for all this with filament lamp in our syllabus, semiconductor diode, and metallic conductor. I'd highly recommend that you memorize this and you know how they work, right? But the resistance of a filament lamp actually decreases, right? That's why this ratio is actually going to the resistance of filament actually increases, right? So the ratio of IV will actually decrease. That's why it's going to be a curve that's going to be like that, right? But again, I highly recommend, look at this axis, guys. If this is an IV graph, it makes A correct. But if this was a V, again, it's an I graph. This is just like this graph flipped, so it would make D correct. So whenever you see these questions regarding filament lamps, always, number one, look at the axis. Is it an IV graph? If it is, that's fine. Move on and find the graph that you need, okay? Two lamps are connected in series to a 250 power supply. Guys, draw graphs, draw diagrams. Try to make these things more conceptualized. Don't just try to tackle these questions without drawing. Draw a power source, right? So let's draw a power source. This is a power source, okay, that has 250 volts, right? Then I connect two lamps, right? This is my first lamp, okay? And this is my second lamp, right? So I go back, they're connected in series. So you tick, right? Are they in series? Yes. 250 volt supply, yes. One lamp is rated 240 volts. So one lamp is 240 volts and 60 watts. The other lamp is rated 10 volts and 2.5 watts, right? So if I want to find the current here, I basically know that power is basically VI. So, and the current over here will be my power, which is 2.5 divided by 10, which is 0.25 amps. The power here will also be 60 divided by 240, which is 0.25 amps, right? So the current flowing through here is actually 0.25 amps. This gets 0.25 amps, and if I say 240 plus 10, that's actually 250, which I actually have over there, right? So 240, they all get the same current. Everything is fine. The potential difference is fine. So both the lamp will just light at their normal brightness, right? Why would they light less than their normal brightness? It doesn't make sense, right? Because this will light up and this will light up at their normal brightnesses. Why would it light less brighter? Get this. It can light less brighter. Maybe the current is less, right? Maybe the voltage is less. But from this circuit, I have 240. I have 250, sorry, as my power supply. If I have 230 as my power supply, I might say, yeah, sure, maybe it won't light as brighter. But everything is met. Every light is going to get its voltage and everything is going to get its current, right? Only the 240 V lamps. Why would it only light if current is flowing through both of them, right? So C doesn't make sense. A doesn't make sense. And D, the 10 volt lamp blows. Why would it blow, right? What is it done wrong? It can't just blow up because everything is in order. So it can't be D. Question 34. Which equation is used to define resistance? Resistance is basically the potential difference is equivalent to current times resistance. Yeah, the answer is B. That's basically the definition that we use to define resistance, right? The ratio of potential difference to the current. That's basically resistance, right? Moving to question 35. The charge that is a fully charged 12-volt battery can supply 100,000 coulombs, right? So basically, Q is actually 100,000 coulombs, right? The start of a motor requires a current of 200 amperes for a period of two seconds. So we know that Q is basically IT. So if it's 200 multiplied by 2 seconds is going to be 400. So this starter, as you can see over there, that's the starter of a motor, right? So that starter of a motor requires a current of 200 amps for a period of 200. So it needs 400 coulombs of charge on average, and the battery will not recharge. So how many times can I start it? So it's more like this. You start the car, you take 400. You start the car, you take 400. You start the car, you take 400, right? And you don't recharge the battery. So how many times can you keep on doing that? How many 400s can you take from 100,000, right? So it's basically 100,000 divided by 400. That's 250. So it's 250 times that you can keep on taking 400 until it says, no, I'm done. You've exhausted everything. The starter will not start because you're not recharging the battery. Of course, you're not going to get, a constant supply of 400 all the time, right? I'm moving to question 36. We're given a potential divider circuit that is formed by connecting a battery of negligible internal resistance in series with two variable resistors, right? Variable resistor Rx and variable resistor Ry. Okay. Which combination of changes must cause Vx to increase? Get this, guys. Potential difference, EMF, all these concepts, they are based on resistance, right? So the PD is related to the resistance, right? How so? The bigger the resistance you have, okay, the bigger your resistance, the bigger the PD that you get, right? I always give this example. Imagine you have a bag of sweets, right? And you're distributing it amongst two people. Then you say to them, no, the criterion that I'm going to use is age. The older that you are, the more the sweets that you get. So person A is older than person B. They'll basically get more sweets because of their age. You could ask, why not current? Why not this? You could ask, why not the height? Why not? But the criterion has been set. It's going to be their age. In a similar way, the criterion is already set. It's resistance. The bigger the resistance you get, the greater the potential difference you're going to get. So basically, if I increase Rx, that will cause Vx to increase. But if I increase Rx, Ry must also be smaller. Okay, so Rx is going to be larger and Ry is going to be smaller. So again, in my same example, if you want person A to get more sweets, what are you going to do? You're going to increase their age, if that was possible, make them older, right? And make person Ry smaller, younger, because they'll get smaller and they'll get the biggest sweets that will be there, right? So in a similar way, you have to increase the resistance of Rx and decrease the resistance of Ry so that Rx gets more, because that's the criterion, right? The bigger the resistance that you have, the bigger the potential difference that you're going to get. It's simple as that. That's how current works. You have a bigger resistance, we give you a bigger potential difference, right? Very important. Moving to question number 37. We've been given a potentiometer, right? And we've been asked to find the maximum range of the output voltages. Get this, guys. Whenever you're given a potentiometer question, there can only be two possible situations, right? I would highly recommend you try a lot of these questions of potentiometers and you realize this common trend. They will always, if in terms of output voltages, you only have two maximum positions. The first one is at the starting point. So let's go here. The first one is here at the starting point, and the last one is at the finishing point, right? So what can I do? Let me remove this here and put it at the starting point, right? So let me remove this. Okay. So get this, guys, right? That's how potentiometers work. You only have 2 points that you can deal with, right? So let's remove this this thing over here. Okay, so let's remove it. Okay, and let's place it over here. So our first scenario, we're going to place it over here, right? So if you place it over there, you're going to realize one thing, right? If you place it over there, you're going to realize one thing, that the output voltage that you're going to get is because of this 2 ohm resistor. Because remember, like I said, the output voltage that you get is based on the resistance that you have. That's a law. So the output voltage that I'll be getting here, so Vx that I'll get in this situation will basically be, how much do you got? You got 2. Okay, what's the total? 2 plus 3 plus 4 and multiply by 9. What do I get? I get 2, right? So this will get 2 volts, right? So that's case 1. So with potentiometers, especially of this kind, you only have 2 cases, right? So the second case is we're going to remove it again, okay? And we're now going to place it over here, right? We're now going to place it at this end over here, right? And when we place it at that end, I want you to realize what's happening here. And when you place it at the end, I want you to keep track of what's going on here. We now have 2 and 3 combined together. So for case 2, okay, just going to be simple. 2 plus 3 divided by 2 plus 3 plus 4 multiplied by 9. That's going to give you a value of, okay, that's going to give you a value of 5, right? So the range will lie from 2 to 5 volts, right? So that's what you need. With potentiometer questions, especially of this kind, you have 2 conditions, your maximum and your minimum. If it's at the maximum, if this wasn't there, let's assume this wasn't there, right? So let's say this wasn't there, and it was just one continuous wire like that, right? It would mean that if I'm at this position, I have 3 over 4 times 9. That would be my output voltage, right? My second other scenario will be putting it over there, right? My second scenario will be if I place it over here, it will be 0. because there is no resistor that is over here. So it will be 0, right? So that's how you need to think of potentiometer questions. Move it 2 points, the maximum and the minimum, especially potentiometer questions of this kind, right? Very important. Moving to question 38. What are the nucleon number and proton number of the nucleus formed by this decay? So it undergoes alpha decay. So basically we have 185, 79 AU, right? And it undergoes alpha decay. So it's going to lose 4. So it's going to be 180, 81. And that's going to lose 2. That's going to be 77. And that's going to be, what is it forming actually? No, we just say X plus 42 alpha plus some energy, right? So it's 77, either B or C. And if you subtract 181, oh, sorry, they just said the nucleon number. Okay, so the nucleon number here would be C. But one of the tricks that they usually put is they would say neutron number. Okay, and most people would just say 181. Not realizing that neutron number is the difference between the proton number and the nucleon number. Like what I was about to do. Like I was just about to subtract, not realizing that I haven't read the question right. It's supposed to be nucleon number or neutron number. So be very careful on this question particularly. Question 39, which row gives the correlate classifications of protons. Protons are hadrons. What does it mean to say they're hadrons? They experience the strong nuclear force, right? So protons are hadrons. Electrons are leptons, sure. They do not experience the strong nuclear force. Neutrinos are also leptons, so it can't be A. Sorry, it can't be A. Move on to B, right? Protons are hadrons, leptons, so the answer is B. But question 40, which equation represents beta plus decay? Here's my trick. Whenever you see the word beta plus, right? So beta plus decay basically means positive, right? Okay, right? And beta negative is basically negative, okay? Right, so this is the trick that I was talking about, right? So for positive, because positive starts with a P, okay, look at this, positive starts with a P. So you just need to start, what starts with a P? It's proton. Automatically, proton goes to a neutron, right? You've already started your brain to initiate, right? Then just know if it's proton, neutron, I just need a positron, right? This will just be secondary information, right? You need a positron, then you need a neutrino, right? This will just be secondary information, right? And beta negative particle starts with an N. Automatically, what comes to your mind? A neutron, right? A neutron will turn into what? A proton. And the proton will give you an electron. And the electron will give you an anti-neutrino. Okay, that's very important. So the answer will be D. Thank you guys for watching. I hope it was really helpful. And if there's anything that was quite unclear, I'd highly recommend that you put it in the comment section so that I can be able to respond and be able to address any misclarities. And if there's an error, I could have made an error on any particular question, feel free to actually say you have made an error on this particular question. And guys, I really recommend with paper ones, study the whole syllabus. They ask almost everything, every concept, every little concept, right? As you can see, there's basically all the concepts in electricity, right? A bit of waves, everything. They really want to test how much you have really understood. Thank you guys for watching. I'll see you in the next one.